When we think about the Apollo mission, we think about the Saturn V rocket, that massive roaring pillar of fire. We think about the brave astronauts who gamble their life for the curiosity of humanity. We think about the sheer physics of escape velocity. We assume the hard part was the rocket. Let me tell you something interesting. Getting into space is just chemistry, but landing is math. In 1961, when Kennedy promised to put a man on the moon, the lunar module was too unstable. The astronauts just couldn't fly it manually. They needed a digital autopilot similar to modern day autopilot systems in the aeroplanes. And the math required to guide the spaceship in real time didn't just require a computer, rather, it required a computer that didn't exist. Computers in 1960 looked something like this. They were size of rooms, they sucked up enough electricity to power up the whole street. And if you wanted to ask one question, you punched holes and waited one whole day just to get an answer. NASA had a problem. They needed a power of room-sized computer, but they had to shrink it down to a size of suitcase, and it had to run on a battery. And most importantly, it had to do something no computers had ever done before. It couldn't just calculate numbers, it had to fly. If your computer crashes today, it's annoying, right? You reboot and you lose your Word doc, not a big deal. But what if the computer guiding the lunar module crashes while descending at 3000 miles per hour? You don't just lose a document, you create a crater. When I say the word computer, we would probably think of this or this. We think in terms of screen, keyboards, and internet. If I would ask you a question, how many computers you own, you would probably say 3 or 4 by counting on your smartwatch, tablet, and mobile phone. This might surprise you, but the actual number is likely over 100. The computers that actually keep you alive are the one that controlling your car brake, heart rate monitor, and power grid systems, which you will never see or never think about. If I say the toasters in your kitchen also has a tiny computer inside it, you would probably think, why do toasters need to think? Why did the world's smartest engineer spend 30 years trying to put a small brain inside a piece of bread browning metal? Today, we are looking at the hidden revolution of an embedded systems, a tiny chip that revolutionized the whole world by staying invisible and which also powered the Apollo mission back then. Back in 1960s, if you wanted a computer, you needed a room-sized machine and $1 million budget. But engineers had a dream. What if we could make this computer so small and so cheap so that it can fit inside anything? And the problem wasn't just size, it was integration. The computers needs a CPU which is analogous to human brain, which is involved in doing all the mathematical calculations for us. It also has RAM, which is analogous to nodes which we usually use for scribbling things temporarily. And then we have ROM, which is analogous to a library which plays a role of storing the program permanently inside the controller. In 1970, all the components that I mentioned was separate and it was expensive. It's like you are trying to build a car where engine, steering wheel and the columns were manufactured by different companies and they lived in different cities. During this time, the engineers at MIT made a gamble on some unproven technology called integrated circuit. And these integrated circuits were tiny chips that contained multiple logic gates and they were lighter, faster, and they consumed less power. The hardware was only half the battle. They needed a software. And back in 1965, the software engineering wasn't a job. It was something a woman named Margaret Hamilton had to invent from scratch. She realized that in space, you can't just run a program from top to bottom. The space is chaotic, and she realized that the computers need to switch between the tasks instantly. And this gave birth to the modern concept of embedded systems, and the computer that was used in Apollo mission was called Apollo Guidance Computer, or in short AGC. That moment defined the modern world. The AGC proved that you could trust a tiny silicon chip with the human life. Even today, we use the same logic. That is, real-time priority scheduling is what fires your car's airbag. Even if the radio in your car crashes, your brake still works. That is the legacy of Apollo. We learned to split our mission into critical and non-critical. We went to the moon to explore the universe. In doing so, we discovered the architecture of the modern digital world. The most important footprint we left wasn't on the lunar dust, it was in the silicon. In 1971, while everyone were busy building computers for the desktop, an engineer named Gary Boone at Texas Instruments was building something humbler, a simple calculator. He just realized that if he could include the brain, memory, and the input-output ports into a single silicon chip, he wouldn't just have a computer, rather he would have a microcontroller. This wasn't a general-purpose computer that was designed to browse a non-existent web. Rather, it was a single-function computer. It was designed to do a single function throughout its whole life perfectly. By 1964, Texas Instruments TMS-1000 became the first commercially available microcontroller that didn't just revolutionize the Silicon Valley, rather it created a boom in the appliances sector. And that revolution didn't just stop at calculators, it exploded. From a single chip in 1974 to billions of devices today. Here is the catch. They all didn't just evolve into a single thing. Just like animals evolved into mammals, birds, and fish to survive the different environment conditions, the microcontrollers evolved into different families to solve different problems. Some of them were built for the raw speed, that is, to do the mathematical calculations fast, whereas some of them were built to sip power so that they could last longer on a coin cell. Some of them were built to talk to the entire world wirelessly. If you open a catalog today, you wouldn't just see a single chip. Rather, you would see AVR, PIC, RISC-V, ESP32 and the massive ARM ecosystem. So how do you choose a microcontroller for your project? How will you know which brain belongs to your robot and which one belongs to the washing machine? So in the next video, we'll discuss about different families of microcontroller and how to choose a best microcontroller for your project. I am Vinod and this has been the story of the computers that run our world. Thanks for watching. See you in the next one.